Namaskar and hello. Welcome to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects by clarity of concept and right understanding. Today in our playlist Class 12th Physics and Physics Made Easy, explain few more multiple choice question patterns of electrostatics which are really very important for all type of competitive exams. Let's start. An uniform electric field is produced between two parallel plate, one of which is grounded and second got plus V potential. So in this area a uniform electric field of identical magnitude and direction is produced. Now a charged particle of mass m and charge q remain stationary in this electric field. That means force of gravitation on mass acting vertical downward and force of electric field on charge acting vertically upward are equal and opposite. Now the charge of this particle is reduced to half, that is from q to q by 2, and this potential is changed from plus v to 1/5 value v by 5. Then we have to find out net acceleration on this particle in initial condition with q amount of charge and v potential difference between plates. The electric force on q charge by uniform electric field between plates QE is equal to gravitational force mg. Now for parallel plate, the strength of electric field is potential gradient or potential coming across unit displacement between plate. So when we divide potential difference with plate separation, we will get strength of electric field. Since in changed condition with same plate separation, potential has reduced to 1/5 value, the new electric field in changed condition will become 1/5 of previous value. So new electric force with half amount of charge and 1/5 electric field become 1/10 of previous force. Previous force is equal to mg. So new electric force vertically upward become 1/10 of previous mg force. So net force acting downward, difference of mg and 0.1 mg become 0.9 mg, and that will produce vertical downward acceleration of 0.9 z meter per second square in this system. Today in this learning video, we'll discuss several question patterns related to motion of test charge particle in uniform electric field. In this example, the electric field is directed normal to initial velocity of charge particle, and in those conditions when electric field and initial velocity got an angle other than 0 or 180, charge particle trajectory become a parabolic trajectory, and it is one such example very important from examination point of view. Again, between two parallel plate, an uniform electric field is produced in this space, but we won't know its direction. If upper conductor plate is positively charged or at positive potential, then electric field will be directed vertically downward or vice versa. Now two charged particle, one proton, one electron of identical charge but of opposite polarity but different mass, enters in this uniform electric field with same uniform perpendicular initial horizontal velocity. When electric field of red arrow direction won't have any component along initial velocity of charge particle, then this initial velocity component in horizontal direction remain constant and charge particle will travel this L distance of plate width in L by Vx time, but at the same time this electric field will produce force and acceleration along its direction on positive charge and in opposite direction to negative charge, and amount of acceleration is given as force, charge and electric field product divided by mass. In this uniform electric field, strength of electric field is the same, so acceleration become proportional to specific charge or charge to mass ratio, and for all charge particle, electron got lightest mass with charge or highest charge to mass ratio. So in such circumstances, electron will have highest acceleration as compared to other charged particle, and in fact higher charge to mass ratio will have higher acceleration. Now there is no initial velocity along direction of electric field that we call y direction. So with time, acceleration generate velocity along y direction and produce displacement as per law of motion. Y is equal to ut plus half at square, and there is no initial velocity in y direction, so it is half at square. Now time taken to cross electric field of width L by initial Vx velocity is L by Vx, since both L and Vx is constant. So this time taken is also constant. So amount of y displacement directly depends upon acceleration, which depends upon charge to mass ratio. And since electron got higher charge to mass ratio, so electron will have higher amount of displacement. So it either occupy A position or D position depending upon direction of electric field. And here we got A and D choice. Now if electron is at A position, proton must take opposite displacement and occupy lesser displaced position C. So A with C would become a right choice, and D with B could be another choice if electric field is in opposite direction, but that choice is not given here. So in this example, upper plate is at positive potential, electric field is acting vertically downward, and proton being positive got force and acceleration along direction of electric field, and being higher amount of mass or smaller amount of charge to mass ratio, it would have smaller y displacement, so it will occupy C position. And electron being negative charge move opposite to the direction of electric field and got higher amount of y displacement due to higher amount of specific charge as depicted here. So this option 4 is the right choice. This question is an example of straight line motion, as here instantaneous velocity and instantaneous acceleration of electric force both are acting on the same line, and we have to find out ratio of kinetic energies of proton and alpha particle if both are accelerated in same uniform electric field for the same time. So ratio of kinetic energy of proton and alpha is to be calculated when in an uniform electric field of strength E, charge Q have a force QE, and force divided by mass would become acceleration, and acceleration depends upon ratio of charge to mass in uniform electric field. And since motion is for certain amount of time, then particle velocity, which is initially 0 in acceleration A, after t time become at, and since t is constant for both particle, velocity acquired by acceleration in t time become proportional to charge to mass ratio. And kinetic energy of a particle is half mv square, where velocity is proportional to charge to mass ratio, so velocity square is proportional to q by m square, and kinetic energy ultimately become proportional to q square by m. And for proton and alpha, ratio of kinetic energy, proton got 1 unit charge of 1 electron and 1 unit mass, so this is charge square to mass of proton, and alpha got 2 proton 2 neutron, so charge of 2 proton square divided by mass of 2 proton plus 2 neutron, that is 4 unit. And if we solve this ratio, it comes as 1:1. That means both proton and alpha in this particular case, when accelerated for same time in same uniform electric field, will acquire same amount of kinetic energy, though velocity of 2 particle in q by m ratio got a ratio 2:1. Proton got double velocity than alpha, but since alpha is heavier particle, so the kinetic energy of both will be the same. If particle of previous example, proton and alpha travel in the same uniform electric field for the same distance, then we have to find out a ratio of their speeds and a ratio of their kinetic energy. Again, when a charged particle experience force in electric field, acceleration become proportional to charge to mass ratio. And since we have to make ratio calculation for same travel distance, so we use this expression of law of motion, where velocity after s amount of travel distance is given as initial velocity square plus 2 times acceleration into displacement. Since initial velocity is taken as 0 and displacement of both proton and alpha is the same, then velocity square become proportional to charge to mass ratio. So velocity is a ratio of root of charge to mass ratio. For proton it is 1 unit charge, 1 unit mass, and for alpha it is 2 protonic charge and 2 proton and 2 neutron, 4 unit mass. And if we make this ratio calculation, it is 1:1 by root 2 or root 2:1. So option second is the right choice. To find out ratio of kinetic energy of proton and alpha in the similar conditions, we can use amount of work done by potential difference on charged particle by electric field, which is product of charge and potential difference, and that work done get converted into kinetic energy of particle. And since potential difference is strength of electric field intensity and displacement along electric field, and since particle travel for the same distance, s is constant, electric field intensity is also constant for both particle. That means kinetic energy become proportional to amount of charge, and since alpha got double amount of charge. So kinetic energy of alpha is 2 times of kinetic energy of proton if both travel for the same distance in the same electric field. We have given that two charged particles of mass m and 2m have respectively charges q and 8q. We have to find out the ratio of their velocities if both from rest moves under the same potential difference. So potential difference perform work on charge particle, and potential difference is work done per unit charge. So amount of work done on q charge when it move by a potential difference v is qv, and that get converted into kinetic energy of particle if it starts from rest, and kinetic energy is half mv square, and here v square is proportional to q by m, as accelerating potential v is the same for both particles. So v square ratio for one particle of charge q and mass m and second particle of charge 8q and mass 2m is 1:4, and if we take square root, then velocity ratio will become 1:2. And if someone has asked ratio of kinetic energy of these particles, then that kinetic energy is directly proportional to amount of charge for the same amount of accelerating potential, and the ratio will become 1:8 for these two particles. This example is really interesting and of higher difficulty order. We have given that proton and alpha are placed at a distance r on a frictionless plane and they are released. So mutual repulsion between these two positive charge will repel both these particles and they will move apart. We have to find out kinetic energies of these particles, in fact of alpha, when these two particles are very far away from each other. Now this charge system at a certain distance r got certain potential energy, and we can find out potential energy as amount of potential established by one charge, say proton of E charge at r distance is k E by r, and in this potential when we bring alpha from infinity having charge 2e, amount of work done become potential energy of this system. So potential energy of this system is 2ke square upon r. When these two charged particles move very far away from each other, this potential energy becomes 0 and get converted into kinetic energy of these two particles. But the kinetic energy is not shared equally among these two particles because we have to obey conservation of moment also. So both these particles which are stationary initially, so initial moment of this charge system is 0. So in any condition afterwards, the two particles should have equal amount of moment in opposite direction to make conservation of moment. Now kinetic energy, which is half mv square, can be converted in terms of moment. When we multiply m at numerator and denominator, the numerator become moment square, and this kinetic energy can be written as moment square divided by 2 times of mass. And since moment of the both particle numerically is the same, of course in opposite direction, then kinetic energy become an inverse function of mass, and proton and alpha got mass in the ratio of 1:4. So their inverse kinetic energy ratio is 4:1. So the total energy 2ke square upon r should be divided in 5 parts, and one part is 2 by 5 ke square by m, that is possessed by alpha, and 4 part of that, that is 8 upon 5 ke square upon r, would be kinetic energy of proton in this case. There could be some questions of circular motion of charged particle in electric force systems, as in this example, as stationary source charge plus q is situated at this position, and from r distance of it a negative q charge got an electrostatic attraction force, and this charged particle of mass m when moves with v tangential velocity will have centrifugal force equal to centripetal force and equilibrium established as circular motion. Now in this case we have to find out relation of time period of circular motion with this radius of circular orbit. So as per force equilibrium, the electrostatic attraction force among test revolving charge and central stationary source charge is k small q capital Q over r square, and it must be balanced by centrifugal forces mv square by r. Since k small q capital Q and mass of particle is constant, then velocity square become inverse of radius in this circular motion, and in circular motion one periphery is equal to 2 pi r, and if this periphery is traveled by tangential velocity v, then time taken to make one rotation, that is time period, is periphery divided by velocity, and in place of velocity we can write 1 upon root r. So 1 over root r is solved and brought to numerator side. This power of r become 1 and 1 and half, that is 3 by 2, and this can be simplified as t square is proportional to r cube. So that become relation between time period and radius of orbital motion. The similar type of time period and radius is obtained in gravitational circular motion such as of Earth around Sun. Question related to electric field intensity and potential calculation in an electric field of electric dipole are also very important in our examinations. We have given that electric field intensity and potential value at a distance r from center of a dipole on dipole axis, that means position vector making an angle 0 with dipole moment, is respectively capital E and capital V. We have to find out value of electric field intensity and potential at a distance r on quadrature axis, which makes an angle 90 degree with dipole moment direction, this q axis. We know at any distance r from dipole moment with an angle theta, electric field intensity is given by this relation, and for theta 0, this electric field intensity on direct axis become 2 kp upon r cube, and on quadrature axis with theta 90, cos 90 becomes 0, and this figure become kp upon r cube. So strength of electric field become half of electric field on direct axis with the same distance from dipole moment. But the significant fact is that along direct axis electric field is directed along dipole moment direction, whereas on quadrature axis the direction of electric field get reversed. So if this is E at a r distance from dipole moment, then on quadrature axis at r distance electric field become not only half of magnitude but in opposite direction. So answer is minus E by 2, and we have two such options, and final answer will be decided by potential value on quadrature axis, and this is a relation of potential at any r distance with an angle theta with dipole moment from a electric dipole, and on direct axis theta is 0 and potential is kp upon r square, and on quadrature axis when theta is 90, cos 90 becomes 0 and potential becomes 0. So at q axis anywhere whatsoever the distance r from dipole moment, potential is always 0. So this first option is the right option in this question. This is also true as this quadrature axis got a symmetrical positioning with respect to positive q charge and negative q charge, and at same distance and same magnitude positive charge produce positive potential, negative charge produce negative potential, and sum of two potential become 0. So on quadrature axis everywhere potential is 0 and electric field is in opposite direction and got a relation kp upon r cube, whereas at direct axis it is 2 kp upon r cube, and two electric field on direct axis and quadrature axis are opposite to each other. In a similar type of question in an electric field of electric dipole on direct axis where position vector makes angle theta 0 with dipole moment, at r distance electric field intensity is capital E and potential is capital V, and we have to find out electric field and potential at 2r distance on opposite direction of dipole moment with angle theta 180 degree. Electric field intensity from a dipole moment P at a distance r from it at an angular position theta with dipole moment is given by this yellow highlight relation kp upon r cube multiplied by square root of 1 plus 3 cos square theta, and for theta 180 cos theta is minus 1 but cos square theta again become plus 1 and result become 2 kp upon r cube. And one interesting thing, on direct axis theta 0 position positive charge produced being closer to observation position, higher magnitude of electric field shown by a red arrow, and this negative charge produced smaller amount of electric field shown by blue arrow. So resultant electric field of dipole moment is along the direction of dipole moment at theta 0 position. Similarly at theta 180 position this negative charge produce inward stronger electric field being closer than this positive charge, and once again resultant electric field is in the direction of dipole moment. So on direct axis whether it is theta 0 or theta 180 electric field got a relation 2 kp upon r cube, and at both position it is in the same direction. So at double distance due to inverse cubic relation of distance 1 by r cube, this electric field become E by 8 with the same direction. So plus E by 8 is right choice and minus E by 8 is not that choice. Now for potential calculation, this is our relation of dipole moment P at a distance r with angle theta kp upon r square into cos theta, and for theta 180 cos theta is minus 1. So potential is minus kp upon r square, and that is also true being closer to negative charge, potential everywhere in this vicinity is negative, and at axis of dipole at theta 180, this is minus kp upon r square. So if it is v, then at this position of double distance, potential is inverse of the square of the distance, 1/4 with negative sign, so it is minus v by 4. So option 3 is the right choice here. If the same question is asked for r by 2 distance on theta 0 position, then electric field become 8 times of E, 80, and potential become 4 times, that is 4V. We end this learning video with very strong conceptual question: when an electric dipole is placed in uniform electric field and non-uniform electric field, and we have to study its motion and find out correct statement regarding motion of electric dipole. First statement is always perform angular motion in a uniform field is a partial correct statement. In fact, is a wrong statement. The true statement is it can perform angular motion but not always. When electric dipole moment makes an angle with direction of uniform electric field, then positive charge will experience force in the direction of electric field and negative charge experience force in the opposite direction. Two forces of equal magnitude and opposite direction on this rigid system generate a force coupled to rotate this dipole moment along axis of dipole. So for theta angle between dipole moment and electric field other than 0 and 180, dipole can perform angular motion due to electric forces. When dipole makes angular motion and get its alignment of dipole moment with electric field direction, forces of electric field on two charges plus q and minus q, again equal and opposite, acts on the same line and will neutralize each other. So at this position dipole will remain static or stationary, and this position of theta 0 between dipole moment and electric field intensity is called stable equilibrium. So in theta 0 stable equilibrium and theta 180 when dipole moment and electric field are in opposite direction, unstable equilibrium, dipole won't make angular motion, they remain in equilibrium. The second statement, dipole never perform angular motion in non-uniform field, is again a wrong statement, as whether dipole is in uniform electric field or non-uniform electric field, if dipole moment makes an angle with electric field as in these two diagrams, the two forces acting on plus q charge and minus q charge will frame a force couple and try to rotate this dipole in such a way such that dipole moment will get its alignment with direction of electric field. So whenever dipole moment and electric field got an angle, it will have angular motion. So this second statement is a wrong statement. Both third statement and fourth statement are true statement. Dipole never perform linear motion in uniform field and it always perform linear motion in non-uniform field. Both are true statement. As in uniform electric field, force on this plus q charge and force on this negative q charge are equal and opposite, will cancel each other. So there is no net force to make linear motion whatsoever orientation of dipole moment. But in non-uniform electric field, force in stronger electric field condition is stronger in magnitude than in weaker electric field, and difference of two forces become a net linear force to make linear motion of this dipole moment. So this dipole initially make an angular shift allowing its dipole moment along direction of electric field, and then it will start linear motion in the direction of electric field. So it always perform linear motion in uniform electric field and never perform linear motion in uniform electric field. So if dipole is placed in a field and perform linear motion, then that field is non-uniform, and not perform linear motion, then it is a uniform electric field. That could be test of uniformity or non-uniformity of electric field. We have tried to improve your conceptual clarity about motion of charged particle in uniform electric field and motion of electric dipole in electric field. Our other learning video of same playlist will help you to score high in your competitive exams. We once again appreciate your interest and support to our learning videos. Thank you very much.